Real structures generate damping forces. Damping is a transformation of energy due to opening and closing of cracks, internal energy from strain, internal friction, and friction at connections. There are also many other sources of damping. There are three basic damping cases: critical, undercritical, and overcritical. Critical and undercritical are most commonly observed in structures, and we will restrict ourselves to these cases on this course. Recall that the quadratic that we seek to solve is given by s squared plus s over m times by c plus omega squared. We set that equal to 0. Now that c is not equal to 0, equation 1 has the following solution, which is simply the quadratic formula. S1 and S2 are equal to minus c over 2m plus or minus the square root of c over 2m squared minus omega squared. The criticality of the damping depends upon the sign of the term underneath the square root. For critically damped systems, the term under the square root is such that c over 2m is equal to omega. For later use, we define the critical damping coefficient Cc, or C subscript c, as 2 times by the mass times by the natural frequency. If we substitute equation 3 into equation 2, we find then that it has the solutions S1 and 2 being equal to minus c over 2m, which is equal to minus omega. This gives a solution for S1 and S2 with real repeated roots. A suitable form for a solution for u of t is therefore ut equal to g1 plus g2t times by the exponential function st, or g1 plus g2t times by the exponential function minus omega t. To proceed, we need to now specify G1 and G2. To do this, we just need to apply the initial conditions, which in this case are u0, u.0 at time equal to 0. And we note that the velocity is just at the derivative, which is given by g2 exponential minus omega t minus omega times by g1 plus g2t times by the exponential of minus omega t. If we then use equation 7 in equation 6, we can see firstly that u0 is equal to g1 And then using equation 7 in equation 8, we can see then that u dot naught is equal to g2 minus omega g1. So we can then say that g2 is equal to u dot of naught minus omega u naught. Equations 9 and 10 in equation 6 then give ut equal to u naught plus the initial velocity plus the natural frequency times by the initial displacement times by t, all times by the exponential function of minus omega t. We can simplify this as the initial displacement times by 1 plus natural frequency times by time plus our initial velocity times by time, all multiplied by the exponential function minus omega t. Again, we know what our initial displacement is, we know what the natural frequency is, we also know what the initial velocity is. As a result of this, we can plot the response. So in this case, we have our initial displacement and our initial velocity, and we note firstly that there are no oscillations, about 0. So we can conclude that this is the smallest amount of damping for which no oscillations occur in the free vibration response.